I'm now going to explain the interpretation and use of mean squares in analysis of variance to test hypotheses. And to start with, I'm going to use a one-factor example. And it's illustrated in this diagram here. There are 3 experimental treatments and 3 replicates in each of those treatments. And what is recorded in each case is the number of animals that remain surviving in the different experimental plots. So you can see in the first treatment 13, 7 and 15, then 1, 4, 5, 15, 9 and 12 in the third of the experimental treatments. Now before going on to look at the analysis of variance of these results, let's start by looking at simple summary statistics. And I've calculated these in Minitab. So what we've got, the number of observations, which is obviously 3 for each treatment, the mean number of animals remaining, which is 3 1/3 for the algae treatment, and about 12 for the other 2 treatments, and then in the last column, the variance, 4 1/3, 17 1/3, and then 9 for the last treatment. Now, before moving to the analysis of variance, I want to do a little calculation here with the variances. So let's take 4.33 plus 17.33 plus 9 and work out the average. So I'll divide that value by, and the average that I get there is 10.22. So just remember that. Okay, then over on this page I've got the analysis of variance done using the general linear model option in Minitab. And up top here we've got the analysis of variance table itself, adjusted mean squares, F value and P value. And the P value there is less than 0.05, so there is a significant difference among the experimental treatments. In order to determine which treatments would differ, we would need to do the Tukey's test, for example, or some other multiple comparisons procedure. I'll come back to that later on. Let's go and look at what the mean squares mean within the analysis of variance. What I've done here is to tick the option for the results for the analysis of variance that gives us the expected mean squares. And what this is, it's telling us what each of the mean squares is estimating. So one thing you've got to remember is that these numbers here actually mean something. And the easiest way to interpret or to understand that is to look at this number there. As you'll see, that's 10.22. That's the same number we calculated a little while earlier as the average variance. And the variance, remember, is the variability among the observations within each of the experimental groups. So the mean square here is just average variance. Now, in cases where the design is unbalanced and there are different numbers of replicates in each of the treatments, the average variance and the mean square for the error can't be worked out in the simple way I did with the calculator there, just adding up and dividing by 3. It's a slightly more complicated calculation which takes into account the number of observations in each of the experimental groups. But the basic message here is the mean square error is just an estimate of variability among replicates. And if we look at the table down here, this little number 2 here is just referring to that mean square error. So in other words, you can interpret that 2 in the brackets as being equivalent to 10.22. And it also turns up there. So the treatment mean square estimates error mean square plus something else, plus an extra bit. That extra bit there is Q bracket 1. Now in Minitab, square brackets are used to surround terms that are fixed, and rounded brackets or ordinary parentheses are used to surround terms that are random. So the error term 2 is a random error term, is random by definition. In this case, the treatment term is fixed because there are 3 experimental treatments which I set up and I decided to use within the study. So the mean square for treatment here is made up of 2 different bits of variation. The first bit of variation is just error. The second bit of variation is any treatment effects or any differences among the means of those 3 treatments. If that bit there, Q bracket 1, is small or equal to 0, then that's effectively saying that there are no treatment effects. There are no differences among the means of the 3 experimental groups. And if that's the case, then these 2 numbers here, those 2 mean squares, the treatment mean square and the error mean square, will be 2 different estimates of the same number. They won't both come out to be exactly the same. So the bottom one, the error, is 10.22. The top one, if there's no actual difference among experimental treatments, the top one will be around about 10.2, but it might be a bit smaller and a bit larger. If we divide one term by the other, or that mean square by that mean square there, we should get a value of around about 1 if there is no effect of the experimental treatments, because the top mean square, the treatment mean square, and the bottom mean square, the error mean square, should both be around about the same. And that's the entire rationale for analysis of variance. In cases where there are more than one factor and where some of those factors are random, the nature of the expected mean squares gets a little bit more complicated, and that's an understatement. So here is one such more complicated case where there's 3 treatments or 3 effects: location, treatment, and site. The site effect is nested in location, and it is also a random effect. We've still got mean squares over here, and each of those mean squares is going to estimate actual values from the data. The bottom one, as before, is just an estimate of error. So in this case, the error is 0.00416. That's the variability among the replicates in each of the combinations of location, treatment, and site. As with the one-factor analysis of variance, we construct F ratios by dividing one mean square by another mean square. And what we're trying to do always is divide the mean square for the effect we're interested in by a mean square that has everything but that particular effect. So in other words, let's look at the treatment by site interaction here. We want to test whether that interaction is significant. And to do that, we divide the treatment by site mean square by a mean square which has everything but the treatment by site effect. Now the treatment by site effect here is labeled 5 by Minitab. It's in brackets over here because it's a random term, and it's multiplied by 3 because that's the number of replicates. And to test for effects of the treatment by site interaction, we're just going to divide that mean square by that mean square, or in other words, that one by that one up there, which is 0.089 divided by 0.04, which gives us a value of around about 2.16. And Minitab goes and gets the p-value associated with that from the F distribution 0.105, it's not significant. The same applies to testing all of the other effects, but it gets more complicated with the main effects. So for instance, if we look at the location effect, which is 1 in here, in order to test for effects of location, we need to divide this mean square by some other mean square that has everything but the location effect. Now that is the location effect there. It's in square brackets because it's a fixed effect. It's the main effect of location, 1, but it incorporates some effects due to interactions with treatments. And to test for effects of that, we need to divide that mean square by this one here, because the site mean square has everything in it except that bit there. So that bit and that bit are the same, and that bit and that bit are the same, that bit and that bit are the same, but this bit here is missing. So we divide that mean square by that one, or up here, divide that mean square by that one there. And if we divide 0.755 by 0.01, we get a large F ratio, 17.47. P-value, that's 0.014, so there are significant differences among locations. The table down the bottom here actually just estimates the value or the magnitude of the random effects. There are no estimates in there for the fixed effects. That table down the bottom there gives you the error terms that are used for testing those terms there. So the location is tested over the site by location. Treatment is tested over treatment by site, as is site, and location by treatment, and then lastly the treatment by site is tested over the error term itself. Now, what about testing for differences among means using Tukey's test? Okay. There. So Tukey's test is done by calculating the smallest significant difference or least significant difference between a pair of means. And that's the value here. These are data used from an example. So I've called it SSD here. It's also commonly called LSD. We get that value by multiplying a value from the Q tables or the studentized range tables by a standard error. And the standard error in this case is calculated like this. It's the square root of the mean square that's used as the denominator of the relevant F ratio divided by the number of observations in each of the means being compared. So if we go back to our analysis of variance, and if we want to test for differences among locations, that's the F value, and that there is the actual mean square that's being used as the denominator to form the F ratio, because we're dividing this one by this one down here. So over in our formula over here, this is not mean square error, it is mean square site. So that goes in there. In here, we would include the total number of observations used in each mean. So again, if we go back to the analysis of variance, if we calculate averages for locations, then the n is not going to be 3, the number of replicates. It's going to be 3 pooled over the 2 treatments and the 3 sites at each location. So the number of observations in each mean is actually going to be 18. So we calculate standard error from that and use that in the Tukey's test. Minitab is doing an equivalent procedure, but using it to calculate differences between pairs of means and to indicate whether or not they are significantly different. This is the underlying procedure that Minitab is using. Okay, I hope that's of some assistance.